Today we're going to take a huge step forward in our understanding of vectors. So far we've been living in a very 2D world, the flat world of just the x and y axes. That world has served us very well. We've learned how to represent vectors, add and subtract them, calculate their magnitude, and even use the dot product to understand angles and work. But here's the truth. Real life isn't in 2D. Planes fly through the air, satellites orbit above us, forces act in space. Engineers, physicists, game developers, and animators all use vectors in 3 dimensions, and that's where we're headed today. So what does that mean for us? Well, we're going to introduce a third axis, the z-axis, and see how it changes the way we represent and work with those vectors. We'll write vectors in triples like x, y, z instead of doubles, x, y, and discover how all of our familiar operations, addition, subtraction, magnitude, scalar multiplication, dot product, still work, just with that extra dimension added in there. And most importantly, we're going to unlock a whole new way of visualizing space and solving real-world problems that can't be done in 2D. And if you're wondering, will this get confusing? Don't worry. Actually, everything you've already learned will come with us. We're not starting over. We're just evolving. So today, we stop drawing arrows on a page and start thinking like physicists and engineers. Welcome to 3D Vectors, where math meets space. So now that we've had a little introduction, let's think about how we could plot the point 2, 3, negative 4. Well, we're going to use a 3D system with the x, y, and z axes. And each point is written as an ordered triple. So instead of being an ordered pair, now we have ordered triples. The x value is still my first value. The y value is my second value. And now we have this third dimension added. So my third value will be my z value. Now, this is what it looks like in general, just right here, if we were to draw it out. And the way that we keep things straight is using a right-hand rule. I know that any of you that have taken physics would be familiar with some of these right-hand rules, but this one's a little bit different. This one's going to help us keep track of which direction is the positive x, which direction is the positive y, and which direction is the positive z, because when we go to plot these points, we need to know what direction we're going if the points are positive or negative. So mathematicians generally use the right-hand coordinate system, the fingers of your right hand. And so that's what this is showing here. So the fingers of your right hand are going to curl towards the positive x-axis. Your arm then is going to be in the direction of the positive y-axis, and your thumb pointing straight up, or if you're looking down at it, will be the positive z-axis. So I've drawn it, or I've shown it in a program called GeoGebra. That's this image over here on the right. And we're going to pop over there now, just so I can show you in 3 dimensions what this actually looks like. So this should help you visualize a little bit better what's actually going on. You can see we've got the x-axis in red. The positive x-axis is coming sort of to the left and out of the page. The positive y-axis, or the y-axis in general, and this is done in green, and you can see it's coming to the right, where your arm would be if you had your hand in that right hand position. And the z direction is going straight up and straight down. And if I move this around, you can see it. It moves around. I can move it left and right, up and down, and it helps us visualize what is happening in these 2 dimensions. I'm just going to try and get it back around here. So that's what this looks like. And this is the 3 dimensions that we're going to be working with today. Okay, so now that we've laid down that groundwork, let's go back and actually plot the point 2, 3, negative 4. So I've given us our coordinates again, our x, our y, and our z. And remember, the first value will be your x, the second value will be your y, and the third value will be your z. So if we are going to plot these on a 3D space, we are going to start with our x, and we're going to go 2 units in the x direction. Then from the tip of that vector, we're now going to go 3 units in the y direction, the positive y. And remember, the positive y is going that way. So we're going to go If we were right over here, we'd be going 3 units in that direction. But remember, we want it to start from here. So we're going to go out 3 units from the tip of our X component. And now we need to go down 4 in the Z direction. So negative Z is in this direction. So now we are going to go down 4 in the Z direction to get to our point. Well, so that's how we would draw that. Now, what would that look like if we were in 3D? And I'm going to take you back to that GeoGebra and show you. So here's what this looks like plotted in 3D. You can see we've come out 2 in the positive direction on the X. We've gone across in the Y, positive Y direction, 3 units, and down 4 units in the negative direction. And if we move this around a little bit, we can see where this ends up. Now, imagine that we were drawing a vector, a position vector that starts from the origin and goes out to that point that's at 2, 3, negative 4. So it's going to look something like this. And remember, we can calculate the magnitude and the direction. The direction is just the point itself. But we're going to pop back over to the regular screen, and I'm going to show you how we can calculate the magnitude of that vector using what we already know about 2D vectors in 3D. Okay, so here we are back over here to our drawing of it. Now remember what I said, that we can have a position vector that goes from the origin, so from 0, 0, 0 in this case, and ends in that point. Here's our point P that's at 2, 3, 4. 2, 3, negative 4. So this can be written a couple of ways. We can write it just as regular coordinates. So vector U is equal to A, B, C, or in this case, 2, 3, 4. But remember, we can also write it as scalar multiples of the unit vector. And just as a reminder, this is getting messy, but just as a reminder, our unit vector goes 1 unit in each direction. So for our x-axis, my unit vector I with a hat will be 1 unit along the positive x-axis. My unit vector for my y-axis is still j, 1 unit in the y direction. And we are just adding the unit vector k with the hat that goes 1 unit in the positive z direction. So I is the x-axis unit vector, j is the unit vector along the y-axis, and k is the unit vector along the z-axis. So we can write any vector as its unit vector, as scalar multiples of its unit vector. This is this ai plus bj plus ck, because remember, these unit vectors are just the sum of the unit vectors. So if we're adding up a vector, it's just the sum of the unit vectors. So for our particular situation, our vector OP, starting at the origin at O and going to P, could be written then as scalar multiples of I, J, and K. Well, in this case, I have 2 times. So I have 2 times my unit vector I plus 3 times my unit vector j in the y direction plus, minus 4 times my unit vector in the k direction. And it's minus because it's going in the opposite direction. Now, just like we were able to find the magnitude of 2D vectors, we also can find the magnitude of this vector u by using our Pythagorean theorem, because these unit vectors all make right-angled triangles with our actual vector that we're trying to find. So the magnitude of vector u can be found the same way as we found 2D by using our Pythagorean theorem. The magnitude of u is equal to the square root of a squared plus b squared plus c squared. So for our vector u, we have 2 squared plus 3 squared plus negative 4 squared. So our magnitude will be equal to the root of 29, which gives us a magnitude for that vector approximately equal to 5.4. Now, we don't know what units. It was just a point. We could assume it's newtons, maybe. And its direction will just be, in the direction of our point, 2, 3, negative 4. So that's how we can use everything we've already done. Unit vectors, how to write these out, taking what we know about plotting a point in 2D and applying it to 3D. That's what this looks like. Okay, so remember that I said all of our rules for 2D vectors apply to 3D vectors. So that means our vector addition, subtraction, finding the length between 2 points, calculating the magnitude as you just saw, and the dot product are all going to be the same. So let's start taking a look at some examples of that. So if I have a point A that's at 2, 3, 4, and B that's at negative 1, 0, 3, I want to determine 2A minus 3B. We're going to set it up exactly the same as we would have for a 2D vector. So if I have 2 times vector A minus 3 times vector B, then that's going to equal 2 times 2, 3, 4 minus 3 times negative 1, 0, 3. We're going to go ahead and use our distributive property just like we would do anytime we have a bracket and distribute the scalar multiple, or the 2 and the 3, into both of those vectors. So we end up with 2A is equal to 4, 6, and 8. And B is now equal to negative 3, 0, 3. 9. That would be 9. Now we can go ahead and do the subtraction. Just go ahead and do the subtraction. Remember, we're going to subtract our x points, our y points to get our new y point, and our z points to get our new z point. So we would have 4 minus negative 3 for our x point, 6 minus 0 for our y point, and 8 minus 9 for our z point. So that gives us 2a minus 3b is equal to 7, 6, negative 1. We can use the same idea if we're missing values and we want to determine what our missing values here. So in this case, we want to determine x, z, and our missing value of y. So a missing value of x, a missing coordinate for z, and a missing coordinate for y. We're going to set it up exactly the same way. So what do we know? Well, we know x, 2, negative 3, plus 2 times 1, 3, z is equal to 5 times negative 1, y, and 0. We're going to use our distributive property and distribute everything out that we need to. So we end up with x, 2, negative 3, plus 2, 6, 2z equals negative 5, 5y, and 5 times 0 just stays 0. Now we can go ahead and do this. Now we can just go ahead and set it up, as algebra and solve for what we know. So I know that x plus 2, so I'm using my x values, x plus 2 must be equal to negative 5. Well, now it's just straightforward grade 9 algebra. If x plus 2 equals negative 5, then x must equal negative 7. Just rearrange and solve. Let's do the same thing for our y value. 2 plus 6, so here's my y value, 2 plus 6 must equal 5y. Well, 2 plus 6 is 8, so 8 must equal 5y, then y by itself is going to be equal to 8/5, or 8 over 5. And the last one, our z values, we have negative 3 plus 2z equals 0. And now we're just going to rearrange and solve. So 2z equals 3. So z will equal 3 over 2. Okay, so let's try another one using what we already know. This time we're going to use what we know about the relationship between parallel vectors being scalar multiples of each other, and finding the distance between 2 points. So given vector A has point 1, 2, 3, vector B has 4, negative 3, 6, C is 0, 2, 7, and D is negative 6, 12, 1, is the vector AB equal to or parallel to the vector CD. Well, remember that if something is parallel or collinear, as your textbook likes to call it, then one vector will be a scalar multiple of the other. And that's what this is saying. So one vector u will be a scalar multiple, or v will be a scalar multiple of u. And that's what that k stands for. So the very first thing that we need to do in order to answer this question is to figure out the distance between the points. And just as a reminder, if I have 2 points, and we'll just call them in this case A, B, and I want to know the distance between them, I'm taking my x2 minus x1, y2 minus y1, and now because I have a third dimension, I'm taking z2 minus z1. So let's figure it out. So the first thing we're going to do is figure out how long is this line AB. So I have 4 minus 1, that's my x value. My y value will be negative 3 minus 2, and my z value will be 6 minus 3. So this gives me a vector of 3, negative 5, 3. Now let's do the same thing for CD using the same process. We have negative 6 minus 0 for our x value, 12 minus 2 for my y value, and 1 minus 7 for my z value, giving me a vector value of negative 6, 10, negative 6. Direction. I guess we could think of it as the direction. Okay, so if AB is parallel to CD, then CD must be a scalar multiple of AB, and we need to now figure out what is that scalar multiple. Well, we're just going to really take a look at it. So is we could say, is CD some multiple k of AB? And let's take a look and see. Well, I have 3 and negative 6 for my x values. Well, 3 times negative 2 gives me negative 6. Let's check and see if all of them work. Negative 5 times negative 2 gives me positive 10. And 3 times negative 2 does indeed give me negative 6. So we can say that CD is equal to negative 2 of our vector AB, and therefore they are collinear or parallel. Last thing we're going to look at today is you finding the unit vector value, or a unit vector that's in the direction of another vector. So just as a reminder, if I'm finding a unit vector for any vector, that unit vectors wear a hat, little different than a regular vector hat, that is equal to my vector, which will be my direction, divided by the magnitude of that vector. So if we want to find a unit vector in the direction of vector u, then I have my vector u, 4, 5, 6, all over the magnitude. And remember, the magnitude is just equal to the square root of the 3 points. So a squared plus b squared plus c squared. We're just using that Pythagorean theorem. So this one would be equal to 4 squared plus 5 squared plus 6 squared. When the dust settles on that, that's root 77. So we could rewrite our points for this unit vector in the direction of u as 4 over root 77. That's going to be my x value. 5 over root 77, that's my y value. And 6 over root 77, that's my z value. Okay, so that's it for this one. I think it ended up being a little bit longer than what I had intended it to be, but I think we've laid down some good groundwork for 3D vectors. Here's some textbook questions to give a try. If you have any questions, feel free to send me an email.